Welcome to this session that is related with the GHELP project. And I would like to address my first words to give thanks for the people that is behind of this event, but especially to the team that participate in this project that started 3 years ago. So I would like to introduce you about some aspects about hearing loss. As you know, hearing loss is one of the diseases where the World Health Organization take care of, especially from 2017. And this institution remarks 10 facts related with hearing loss, and one of them is addressed to the children. And one of the things that this organization say is the importance of early identification of such hearing loss. So we are working in this field from many years ago, but at the beginning of this project, we understand that maybe it was a very good idea to introduce some tests to diagnose one of the main causes of hearing loss in our country. For that, we understand that 60 to 80% of hearing loss in newborns came from genetic diseases. So if we take in consideration this important prevalence of genetic disease behind hearing loss, the question was, why not incorporate gene tests into early diagnosis of neonatal hearing programs? So in a screening program that mainly is in between 0 to 1 month of life, it's important to have the concept that this screening is followed by diagnosis and treatment, with the final idea to establish an early treatment around 6 months of age. So taking in consideration this flow chart, we understand that introduce hearing or genetic tests in these screening programs, we can decrease the false positive and false negative cases, also reduce losses in person follow-ups, reduce the rate of children referred to diagnosis, provides an etiological diagnosis, and everything that I comment accelerate diagnosis and early treatment and facilitates a personalized medicine in the treatment of disease. And at the end, this introduction of these genetic tests, we understand that also reduce expenses for the health systems. So taking in consideration this hypothesis, we developed this GHELP project with the following objective. The main was drive innovation in the early detection of hearing loss in children by introducing a diagnostic genomic tool in current neonatal hearing screening programs, so as to introduce personalized medicine in the treatment of disease. Also, we have 3 specific objectives. The first one is the clinical validation of a new tool for these hearing genetic diseases in the newborn. So one of the objectives was create a next generation sequencing technology address for this project. The second specific objective was study the financial, social, and healthcare feasibility of including this genomic tool in the current neonatal hearing screening programs for children, so as to propose an action plan that will be announced as programs. I by them reduce the asymmetry in knowledge and innovation in the field of hearing loss in children through training of the different professionals that are involved in this task. So the methodology we used was, from a technical point of view, to develop a 4-work package. The first was retrospective validation of the genetic tool. The second, prospective validation of the genetic tool, training and mobility program, and dissemination of the results. So we established 2 groups. One we call retrospective group, and we study it in the work package number 1. So the inclusion criteria of this group was onset of hearing loss between 0 to 18 years old with pre, peri, or post-lingual deafness. Any type of permanent neurosensorial hearing loss, syndromic or not, genetic or unknown etiology, unknown the phenotype, and post-treatment follow-up of these patients that were included in this group. In the prospective group, we include children at the age between 0 to 3 months with any type of hearing loss that fails the second stage of the newborn auditory screening with ABR or otoacoustic emissions. So in any case, after this inclusion criteria, the family sign informed consent. We collect the clinical data from both groups. We take blood samples and we send to University of Navarra, to THEMA labs, and also to Dreamgenics, just to analyze these samples. So we'll try with this design to have, through the retrospective study, the knowledge about the phenotype of these patients, and also to know the gene mutations in these populations. And in the prospective study, we recruit these samples just to study from a genetic point of view and correlate the findings with the phenotype that came from the retrospective group. So for that, we have the cooperation of a consortium of partners that came from Centro Hospitalar de Lisboa, from CUT Oporto, SHU Purpan in Marseille, no, SHU Marsella, SHU Purpan in Toulouse, Dreamgenics in Asturias, Spain, Biodonostia in San Sebastián, the Instituto de Salud Laboral de Navarra y the University of Navarra in Pamplona. And also we have like associate partners, the Surdos Usuarios from Portugal and FIAPAS from Spain. Thank you very much for your attention. Thank you again to be there. And I would like to introduce the next speakers that are going to speak about the GHELP panel for the genetic diagnosis of hearing loss. But before, I invite you to watch one of the videos that we created at the beginning of the project for dissemination of this project. Thank you very much again.
But what would happen if we weren't able to hear it? What if muting it were not up to us? For some, it starts to be a problem, while others have never heard at all. Through the transnational GHELP project, 8 entities from Spain, France and Portugal want to press play. 5 out of every 1,000 children are born with some type of deafness in southwestern Europe, Sudoe, and it is estimated that in at least 60% of these cases the causes are genetic. If we treat them before 12 months of age, we can get them to hear as soon as possible and to express themselves more easily. Because we have the means for early detection, auditory screening, and now, thanks to this project, a genetic diagnosis panel that can revolutionize diagnosis in babies, advancing knowledge of the cause of hearing loss, thereby facilitating access to their early treatment with current therapeutic options and promoting the development of new curative options within the field of gene therapy. Thanks to everyone who is making this project possible.
Thank you very much. Patricia and Gorka, you have the work.
Gorka, sorry, can you see the presentation? I think you are silenced.
Yes.
You can see
So
it,
hi.
right?
Yes.
Thank you.
So hi, everybody. Thank Dr. Manrique too to give us the opportunity to talk to you a little bit about all the process that we did behind the scenes, on one side. The final goal was to improve the genetic testing for hearing loss. In this GHELP, the development of the GHELP panel was one of the steps. But within the following slide, I would like you to also take a moment to think about how we were a couple of years ago when we started the project. Because this is one of the starting point of all the projects. This reflects, I think, the collaborative idea that we have all of us in mind. This is the scheme that we work on. We have the GHELP hospitals on one side, the ones that were close to the patients, as well as both at the beginning and at the end. And when we created this project, we thought that there were 4 different steps in which we had to all work together to improve the process. And those are the ones that we'll be able to talk now within the following slides. So in the next slide, the key part of the project was there are 6 different hospitals that participated here. But the wet lab protocol, the process of analyzing the samples, was done here at the University of Navarra in Pamplona. So we basically defined some of the input sample requirements and some recommendations to different institutions. Originally, the idea was to only use peripheral blood samples. However, I must say that in the process, we have also incorporated both saliva samples as well as isolated bank DNA samples that some of the institutions had. Within the following slide, I'll focus on the reason why we were planning or proposing to include an NGS-based panel. We talk about hearing loss, but we also know that there are different genes that can have those pathogenic sequence changes that we are looking for. And traditionally, the idea was to test one gene at a time. First, we were testing one gene. If we didn't find anything that could relate with the phenotype of interest, hearing loss in this case, then we'll move to a second gene. Again, if nothing was identified, they will move to another gene. So as you may imagine, this was very long and it was not really proven very successful. Not only that, but we also need to consider that those pathogenic sequence changes can be of different type, and not all the tools that we can have in the lab are able to identify all of them. And just quickly to mention that some of the pathogenic sequence changes can be SNV or indels, and for that we used to use Sanger sequencing. However, in order to identify pathogenic CNVs of copy number variants, we were using other methods like MLPA. However, as we know, there are other panels that have allowed using NGS as a general tool to identify variants in hearing loss as well as in other diseases, given that the tool can allow us to identify all SNV, indels, even CNVs, which could be associated with the phenotype of interest. In this case, will be hearing loss. So then our plan was first select the targeted genes. We used different databases in order to select the final set of genes that we were looking for. We tested both, or the goal at least was to do both nuclear genes as well as mitochondrial genes. And as you can see in the next slide, the approach that we took was to implement NGS enrichment of the regions of interest using some oligos designed by Agilent or provided by Agilent with the following goal: trying to identify or sequence all the coding regions of the genes that we chose, including the splicing site. And also we did include some special regions that were deep intronic or regulatory regions in which we already know that there were some pathogenic sequence changes that had been described. In addition to that, we also added several regions, both on the X and the Y chromosome, nothing to do with hearing loss, but it has allowed us to use them as control regions to identify gender differences between the samples being studied. However, the third part of the step was also another milestone for the project, given that we did implement the wet lab protocol in order to be able to get those blood samples within the lab and then provide sequencing data. But the final steps also had to be worked. That was the bioinformatic work that was done by DreamGenics, especially in two different areas. One, the QC of the NGS data that we provided, just to make sure that all the sequencing data that we were providing was right, followed by variant identification and even annotation of those variants. And then finally, making sure that we all are aware that this is not one hospital-oriented project. There were 6 different centers that provided the samples. So in order to ease the process of interpretation, they also developed a web-based platform that has been essential in order to ease the variant interpretation process. And those two will be the ones that now Patricia will be giving you more information about.
Well, thank you very much, Gorka, and also Dr. Manrique. And as Gorka has just said, I will continue with the 2 key parts of the DreamGenics role in this GHELP project as a bioinformatics partner, which take place right after DNA sequencing and before clinical interpretation by GHELP partners. The first of them is the bioinformatics analysis pipeline. FASTQ files from NGS sequencing are the input for our bioinformatics analysis at DreamGenics. We have developed a specific workflow which integrates different bioinformatics tools and programs that enable an automated analysis from raw sequencing data to the final list of candidate variants for each patient. Briefly, first of all, we perform quality controls of the FASTQ files, as Gorka just has said, as well as gender classification of each sample prior to variant identification in order to minimize sample swaps. Then, the sequences are aligned to the reference genome, and different algorithms are used to identify variants when compared to the reference genome. Finally, we perform variant annotation, where each variant is enriched with complex information from clinical, populational, and functional databases, very useful for final clinical interpretation by geneticists. Once the bioinformatics analysis is finished, it's key to share the data with clinical partners in a way that they can easily access the list of variants identified in each patient. And that would be the second key role of DreamGenics in this project. According to this major involvement, we have developed a specific visualization platform for the samples analyzed for the different centers. We have provided web access to our clinical partners so that they can perform variant filtering, as well as variant review and interpretation. Designated clinical partners from each center have access to the analysis of their own patients. And as Gorka just has said, besides SNV, single nucleotide, variants, and small indels, the visualization platform includes candidate copy number variations too. And as far as we know, it has been helpful in some cases where pathogenic copy number variations have already been defined. It must be said that samples have been codified by CIMA Lab Diagnostics and University of Navarra in such a way that no personal or clinical information of the patient is displayed. Taking them as a whole, thanks to the bioinformatics pipeline and the visualization platform, we can identify variants in patients' DNA located in relevant genes related to hearing loss. All of these variants are noted with information available from multiple databases relevant for interpretation. Thanks to this, clinical geneticists can perform custom filtering in order to enrich for variants of interest and reducing the number of variants to be reviewed until they get to a reduced set of candidate variants for each patient. I would like to thank all of you listening today, all of the project partners, especially Drs. Manrique, Patiño, and Alcorta, and also Dr. Gonzalo Ordóñez, who was previously leading DreamGenix role in this project. Thank you very much, and it's time for the next interview.
Thank you very much, Patricia and Gorka. I don't know if maybe we have maybe 5 minutes. If somebody like to make some comment or questions to these 2 panelists. Or maybe later on we try to keep some room for questions and comments, and maybe through the chat you can tell us these questions. Okay, otherwise, so we move for the next presentation that's into this part of the session related with GHELP project results. So I would like to introduce Raquel Manrique and Heredio Sousa. They are going to speak about clinical validation results of this GHELP panel. Thank you very much.
Good morning, everybody. I don't know if Heredio is around there. I can't see him. Can you see the slide?
Yes, Raquel.
Okay. Heredio, are you there?
Heredio is there. We can see him. And you.
Okay. So I'll start with the presentation, and I'm going to show the clinical validation results. Following the technical steps that Gorka and Patricia were explaining before, I'm going to show the results based on the 493 samples we took. And they are classified, as Dr. Manrique explained earlier, in prospective and retrospective group, depending on the time of sampling. As he said, for the former, patients where NGA sequencing was done as a screening once patient did not pass auditory neonatal screening, and the latter, patients that underwent NGA sequencing if hearing loss is diagnosed and are coming to the follow-up in the clinic. And the genetic analysis is made for the 180 genes analyzed, and for the samples, as Gorka explained earlier, we are doing an analysis based on the phenotype. So if they diagnose any mutations, they classified it as type 1 if it was a benign mutation, type 2 it was likely benign, type 3 it was what we call a VAS, undetermined significance, type 4 likely pathogenic, and type 5 pathogenic. So we consider these two, type 4 and type 5 are the ones that are going to tell us if that mutation is the explanation for the hearing loss in that patient. Among all the 493 patients, 153 belong to the University of Navarra, and we're gonna show the result of our institution. We found 169 mutations among the 180 genes that were analyzed. And look at the, on the lower part, you can see that there were 1,789 variants, in which 67.4% belong to type 1 and 2, 26% to type 3, and a 6.5% to a type 4 and 5 mutation. Here in this slide, you can see the frequency of the genetic variants. So you can see in red, we have type 4 and 5, in yellow, type 3, and in green, the benign type 1 and 2. And you can see each of the genes that are studied in which frequency we show a pathogenic mutation or not. So based on our genetic sequencing, we diagnosed 50 patients of hearing loss out of the 153 we were analyzing in our institution. Most of the mutations were the most frequent mutation, that's GJB2, followed by otoferlin and then MIO7A. In this slide, you can see in the prospective group, we diagnosed 52% of the hearing losses that could explain by a genetic mutation, and among the retrospective group at almost 30%. So now Heredia is going to show you in detail the results for the retrospective group.
Okay. Thank you, Raquel. Good morning, all 104 participants. I'm going to talk, let me share.
Would you like to show your slides?
Yeah, I put my slides.
Okay.
See it? Can you see my slides? Can you see?
No.
Not yet. And now?
It's okay.
Yes.
It's okay?
Yes.
Okay, so let's continue. I'm going to talk about retrospective group at first. When we see the gender of the patients, we see that 29 males, and when we see the distribution of the patients among all the institutions, we can see that Navarra had 132, my center in Lisbon 99, Cufo Porto 68, Diagnóstico in Spain 54, and in France, Toulouse and Marseille 78. When we look to clinical history, we see that most of the patients has no history of the disease, and you can see here But we can see that the perinatal low weight is the most frequent. After we have another prenatal situations, fetal distress, hypoxia, postnatal recurrent otitis media, postnatal ototoxicity, and almost 1% perinatal infection and continuous. When we split the years, we can see that the most frequent hearing loss was the sensorineural profound hearing loss and moderate and severe. And we can see another hearing loss, but in less cases than that I said before. Regards to hearing loss onset, if you see in the left side of the slide, you can see that most of children with hearing loss onset is in between 0 and 2 years, prelingual, and after followed by perinatal, postlingual, and in the hand perilingual acquire hearing loss, onset of hearing loss. Regard to deafness evolution, progression of the hearing loss, we can see that most of the patients had stable hearing loss, and followed by progressive, and more percentage of patients as had another fluctuating and another kind of hearing loss. The average age of onset was 2 years, about 2 years, and you see the maximum average of hearing loss onset was 4.2, and the difference between the onset of hearing loss and the maximum was 2.4 of years of age. And this is in the left side, and if you see in the right side, it's quite similar than the left side. If you regard now to the symptoms associated to hearing loss, we can see that most of the patients had no history of any kind of symptoms, followed by tinnitus. We can see both in left side and the right side is quite similar, 21 versus 19 patients, and followed by tinnitus and vertigo and others kind of symptoms in lower numbers. Most of the patient has normal otoscopy, but we can see that another percentage of patients we can see that in the right side they have another kind of otoscopy, and we can see in the right side of my slide that other kind of disease associated with the hearing loss, and we can see that the most frequent disease was the neurological disease, followed by ophthalmological disease, dermatological disease, and craniofacial features. You can see in this slide another kind of disease associated with hearing loss, but I like that most the patient had no other disease. Regarding to the radiology, the patient did a CT scan or MRI or both, and we can see in this slide that most of them had no malformation at all. But we can see that the most frequent malformation was enlarged cochlear aqueduct, followed by incomplete partition cochlea type 2, and enlarged cochlear aqueduct, cochlear nerve agenesia, and another in less number others malformations. And we can see that when we compare the left side and the right side, the result, the malformation is quite similar. The treatment option that these patients are submitted was submitted. We can see that most of them use the hearing aids, after followed by cochlear implant. We can see in cochlear implant in right side is 162 and the left side is 157. We can see again that the cochlear implant and the hearing aids is the third place of this treatment. Again, we can see that there are other patients that no treatment account about 10% of the patients. Regarding to prospective group, the gender distribution is quite similar than in retrospective group, 35 female versus 27 male. And we can see that clinical history of interest, like in retrospective group, the majority of the patients had no history of any kind of disease. But we can see there is perinatal low weight, prenatal infection, fetal distress, but most of the patients had no history of any kind of disease. So it is important to highlight that the percentage of children with no clinical history was substantially higher in prospective group, 92.68%, than in retrospective group, 83.8%. In our opinion, this data helps to count for the higher sensitivity of GHELP panel in the prospective group versus in the retrospective group. But if you look into the family history of hearing loss, we find that 10 patients, 16.1% patients have a history of hearing loss in their family, while 83.9% do not. This highlights the crucial study of the genetic study. This study that had no history of hearing loss. When we look to the auditory screening evaluation, the screening methodology varied from one center to another, depending on the strategy adopted by the health systems in each of participant regions. In the first phase of screening, 33.9% of patients used autoacuous emissions, 59.7% utilized automatic brainstem auditory vocal potential, and 6.5% failed to indicate the methodology applied. During the second phase of the screening, autoacoustic emission were performed in 24.2% of patients, and automatic brainstem auditory vocal potential in 45.2%, while the methodology used is not disclosed in 30.6%. Bilateral eagle loss pattern was found in 69% of the patients, and unilateral eagle loss was detected in 31%. So it was possible when we look to the cytomegalovirus infection. We see that we test cytomegalovirus in 43.5% of children with a negative result. This information also aids in interpreting the higher sensitivity of the GHELP panel in prospective population versus in retrospective population. Cytomegalovirus infection is the second leading cause of childhood hearing loss in our setting. It is likely cytomegalovirus was the etiology in non-negligible percentage of the children included in this retrospective group, and that went undetected in neonatal studies. This could increase the number of cases of hearing loss of unknown origin and contribute to the inclusion of candidates in the retrospective groups of this GHELP study, thereby decreasing the sensitivity of the GHELP panel in this group and this population group. When we look to the otoscopic results in this prospective group, we see that most of the patients had normal otoscopy, followed by otitis media with diffusion, 2 in the right side and 2 in the left side, left ear. The tympanogram in this patient was normal or type A in 27 patients in both ears. In the right ear 3 and the left ear 2 with the type B or otitis media with diffusion. And 1 patient in the left ear had a type C tympanogram. Regarding to the hearing loss, we can see that the average of the threshold in ABR was in left ear 76.65 and the right ear 79.68. And when we look to the auditory steady state response, we see that most the average of hearing loss is suggestive of the moderate to severe hearing loss. So in the left ear, we can see in the right side of the slide the profound ear loss account 15% and 15 the moderate 11 in the left ear and 6 right ear, and severe 6 versus 7 in the right ear. So in conclusion, we can say that new generation sequencing technology is a reliable tool to diagnose gene variants. Mutation in 168 out of the 180 genes was depicted, and most frequent genes was the GJB2 that encodes connexin 26, and OTOF that encodes the protein otoferlin. Early diagnosis can be made if new generation sequencing technology is established as arbitrary screening. When we see this classification of Shearer et al. Of the hearing loss, we can see that genetic cause account 80% of the hearing loss, versus acquired or hearing loss 20. And GHELP efficiency was 50%, and we got 40% etiological diagnosis in these patients. Thank you for your attention. Thank you, Professor Marek.
Thank you. Thank you very much, Heredio. Thank you very much, Raquel. So at that time, we have the description of the tool, genetic tool that we were using in this project. Also, we speak about the clinical validation of that tool. And now I think that we are going to talk about a very important point, that is the economic impact to use this genetic tool in the neonatal hearing screening programs. And for that, I would like to introduce Marie-Noëlle Camels from Toulouse. So please, Marie-Noëlle. Marie-Noëlle, I don't know if you are there. So
yes, I'm
maybe...
here. Hello.
Okay. Hello.
Sorry, it doesn't work like we want to. It's okay. I share my screen. Is it okay for you?
Not yet. Yeah, no. It's okay.
It's okay?
Yes.
Okay, thank you very much, Professor Manrique. Good morning, everybody, and thanks to all organizers for this meeting. So I'm going to talk about the medico-economic evaluation of the management included genetic assessment of the deaf child after systematic neonatal screening in our region, which is West Occitania in France. So in order to realize this study, this medico-economic study, we started by thinking into the flow chart of care of children after neonatal screening in our region. And we tried to divide deaf children in different cohorts. In our region, the deaf screening is based on 3 screening tests realized in the maternity for 2 of them, and before discharge, and 1 month after for the last one if children remain suspect. The test uses the automated brainstem auditory evoked potential. This is a test recommended by our instances. And after the 3rd screening test, if the child remains suspect, he's referred to a specialized center in order to have the adapted care and diagnosis tests. So when we observe this flow chart, we can isolate it globally 4 cohorts. 1 cohort of suspect child with syndromic evident diagnosis, another one with non-syndromic unilateral deafness, and for the bilateral one of conductive hearing loss, and the last one of bilateral sensorineural deafness. So I have had on this slide the numbers of our systematic deaf screening in 2019, and we can see the numbers of children. At birth, we tested 8 28,000 and more than 700 children. After the first test, we had more than 3,000 of suspects. After the second screening test, only 1,092 suspects. And after the third one, 116 children remain suspect. At least we declare 83 bilateral deaf children. On these 83, we have 58 bilateral and the rest of unilateral deafness. So it's really important to have these numbers in order to think about the best moment to propose genetic involvement and to understand how it's important to repeat screening tests to decrease failed suspects in children. So the big challenge for this medical economic study was the heterogeneity of care according to the type of deafness. And we defined 4 cohorts and try to think about different tests requiring for each cases in order to evaluate its costs. And this during the first year of life of the child. And we divided the first year in 5 periods. I'm not going to give you the price of every test or assessment, but we try to include everything that we have found to be essential for proper management. So you can notice that genetic assessment is systematically proposed. It's really important and an indispensable step of this management for each cohort. So for the first cohort of bilateral sensorineural hearing loss, we propose the genetic assessment around the 4th months. And you can see here that we repeated behavior auditory testing. And we think that this repetition is also fundamental. We included in this flow chart familial partnership, speech therapies, rehabilitation, and radiological evaluations. So you can see in this cohort that the main portion of the costs occurred during the 2nd and the 3rd phases, which represented more than 56% of the total costs. So for the second cohort of bilateral conductive hearing loss, we found a lot of proportion of cerusotitis, and this disease is frequent, and the treatment of cerusotitis permits a high number of auditory normalizations. In this cohort, the genetic assessment is proposed a little bit later, around the 7th month of life. And in this cohort, the main portion of mean costs occurred during the 4th phase, which accounts for 58% to 76% of the mean total cost, depends on the treatment of the cerusotitis. For the last 2 cohorts, management is really different. For the syndromic hearing loss cohort, genetic assessment is proposed yearly, usually during the 1st days of life, and the main portion of the costs occurred at this 1st phase and on the 3rd one, which account for 38% and 55% of the total costs. For the last one, which is non-syndromic unilateral deafness, genetic assessment is less systematic and is proposed latest around the 9th month of life. For this cohort, radiological assessment is really important, and we see that the main portion of healthcare trajectory costs is occurred during the 1st phase, according to 84% of the total costs. So regarding costs, we have observed that in our country, the most expensive unit cost is the genetic testing. In France, the NGS test analyzes more than 200 genes and is usually completed by a segregation test for both parents that add €200 more. You can see here total cost for the first year of life for each cohort with different colors at each care or at each phase of care. For the syndromic cohort, which is a care that costs more, mean annual costs are around 7,000 euros. Then there is a sensorineural cohort with mean annual cost around 5,500 euros. After the conductive hearing loss, with a mean annual cost around 3,700 euros. And the last one, the cheapest, is the unilateral cohort with a mean annual cost around 1,000 euro and 500. So regarding our purpose, which is genetic assessment, and is placed in our flowchart, and more generally, more globally, regarding its place in the screening program, what we know that congenital severe to profound deafness is frequent, is more than 1 on 1,500 newborns. We knew that 80% have a genetic origin, and we know that early management and personalized care is better. So can we use systematic genetic screening at birth? The answer is no, because genetic systematic screening is less effective than audiologic screening, because there is other etiologies of deafness, for example, the fetopathy for 10%. There is no identified gene at all. Only GHB mutation gene is responsible of 20 to 13% of congenital deafness. And there is other genes, but they are extremely rare. And last but not least, we have a weak correlation genotype-phenotype in the field of deafness. So should we use it at birth? The answer in France is no. In France, using genetic systematic screening is forbidden. If we do that, we can modify the relationship between parent and baby when we have pre-symptomatic diagnosis of a hearing disorder that we know appear for years. What do with the results of heterozygosy in healthy individuals? And last, there is big financial and organizational aspects to take into account. Concerning financial aspects, if we use genetic screening before diagnosis, we have several possibilities. If we found pathogenic mutation, it could avoid complete organ assessment and some consultations to decrease costs. So it could be synced, but in France, the price of genetic testing outweighs any savings. In case of pathogenic mutation, given progressive deafness, it's interesting because we can have an appropriate management and follow-up, but it could increase parental concern. If we don't find pathogenic mutations, the management is not modified. However, a more detailed genetic analysis adapted to the child's phenotype could be carried out later and adapted to the particular case. In these cases, the cost may increase. And for the last variants, class 3 or 4, the cost may increase because the damage is not known and the survey is more important. The parent anxiety must also be taken into account and can be difficult to manage. So this project and this whole project gives us big challenges. We have to choose in the right time for genetic testing. I think it's once permanent hearing loss is just obliged, but we don't know, between the second and first month of life, perhaps after the first diagnosis tests are made. We have to reduce in the panel analysis time. It's really important to adapt the care. We have to reduce the price of NGS techniques, seeking to obtain a favorable cost-benefit equilibrium. Then we have to optimize the diagnosis process in uncertain cases, such as variant 3 or 4, to make the distinction between deafness and permanent deafness and middle infection, because we have a lot of normalizations. We have to set in up procedures to rescue cases with a phenotype suggestive or genetic etiology, and implement the support structure for families, particularly when children have progressive hearing loss or uncertain variants. It remains a problem of loss of sight of the systematic neonatal screening. In our country, we have more than 10% of loss of sight. Thank you for your attention.
Thank you, Marie-Noël. So, well, I would like now to show our experience in a different country, different region, and we found some different findings in relation with this topic. So I would like to share my slide with you related with the economic study that we perform in our center. So in general, it's very important to study this point, especially when we try to implement a new tool at the level of the public health system. So I show you here what is the normal algorithm we follow with the newborns that fail the neonatal hearing screening program. So this means that more or less at the age of 1 month, in the first visit by the ENT specialists, we perform different auditory tests just to establish we have a permanent hearing loss. In that cases, we continue this diagnosis process in the second visit, and during that time, more or less at the age of 3-4 months, we continue with different audiological tests. Even we take in consideration the opinion of other medical specialists in syndromic cases, and we proceed to test hearing aids and also to start early stimulation with the collaboration of the speech therapists. And we finish this diagnosis process after the screening process in the third visit at the moment of the 5th to 6th month of age, not only repeating again the auditory test, also we complete with the image tests like MRI and CT. So this is the normal algorithm we follow in children after they fail the neonatal screening program. So in non-syndromic cases, if we apply genetic studies in this moment, when we have hearing loss diagnosed after this first visit, we can save costs related with most of the tests and actions during the second visit. So this means that we can jump to the standard third visit to again repeat the auditory test, to complete the study with MRIs, achieve the final diagnosis early in between 3 and 4 months of age of these children. In syndromic cases, also, it is important the information that we receive with the genetic study apply in this moment, more or less between 1 and 2 months of age. Genetic panel we use in this project reduce diagnosis delays of syndromic manifestation, because we are able to address our attention in relation with the theoretical phenotype we have under the knowledge of the results of the genetic study. So this genetic study reduces expenses for unnecessary medical specialist visits and the tests that they potentially prescribe just to have a full diagnosis of these syndromic cases. And only is very important avoid delays in the diagnostic process. As you know, early treatment is one of the keys of the success in a determinate treatment. So delays increase the poor results, and in this way they increase the social spending in that cases. But also we increase the stress for families because they don't know exactly what this is the diagnosis during a longer period of time, and also increase costs due to the multiple hospital visits during the whole process of the diagnosis. So we take in consideration this algorithm, and we analyze the cost of each of the tests that we perform during this process, and we take in consideration two possibilities. One is the standard neonatal hearing screening program that is in yellow, and the other analysis came from the use of genetic neonatal hearing screening programs as to the standard care we have in this during this process. As you can see, that the direct costs are reduced considerably in this population when we use genetic studies. So in normal conditions in the standard process, the direct costs are around 6,000 euros, and with the use of the genetic test, we reduce 43% of the cost due to we are able to reduce some of the tests, some of the hearing aid trials we have during the second visit in this diagnosis process. So in conclusion, our study has undertaken a medical economic study where the direct cost of diagnosis in a standard program without genetic tests is 5,890 euros, and it falls to 2,567 euros when the GHELP genetic study panel is used in the second stage of an neonatal hearing screening program. This means that in direct costs, 3,323 are saved per child diagnosis with genetic hearing losses. That is 56.41% reduction. In the syndromic hearing loss population, the savings are even more significant. Direct costs are mainly reduced because tests and intervention become unnecessary in the second appointment at the age of 3 to 4 months. The wait time for results and clinical interpretation of genetic tests is vital for the final success of the treatment of that child. Thank you very much for your attention. Now, I would like to introduce Ana Patiño, that is going to speak about the training program that we developed in this project.
Thank you, Dr. Manrique. Can you see my slides?
Yes.
And do they move?
Yes.
Yes, okay. Okay, thank you very much to all the attendees, and mainly to Dr. Manrique, who has been the brain and the heart of this program and this project for all these long years and difficult years also. So it's my part to explain you a little bit about the GHELP training program, about the genetic diagnosis of hearing loss within the context of our project. As you probably know, oops. Oops. So in the training and teaching, learning, dissemination activities are specific and compulsory aims of this specific call of the Interreg Sudoe. So as you are probably thinking, there are plenty of different ways to do this kind of activities, of teaching activities. And I am going just to show you some of them which have been developed within our project. The first of these activities is the meeting of the partners. We began in Lisbon at the very same time that the Eurovision Song Contest. We didn't participate, of course, but the city was wonderful, full of people and songs and music and color. It was a magnificent experience visiting our colleagues in Lisbon. We began there, but then we moved to France and visited our colleagues in Toulouse and Montpellier. And afterwards, the next year, we met in Oviedo with our colleagues of the whole project in the facilities of Dreamgenics. This is because the next year we had a specific GHELP training meeting at the University of Navarra that took place on January 2020, just before the lockdown, here in the facilities of the University of Navarra. And we designed a specific program for the genetic diagnosis of hearing loss in children. You can see here the program. It was a 2-day program in which we had the opportunity to touch different things concerning our project and the diagnosis of hearing loss. Many of them were general aspects in the first day concerning the project, but also general issues about the disease or the hearing loss, and also the techniques. Afterwards, we talk a little bit about technical issues, about you have already heard today, the platform, the analysis, the specific NGOs panel, and so on. And as Raquel Manrique and Heredio Sousa have already talked about, results concerning patients, specific interest in patients, how to obtain the clinical data, and so on. Here you can see my colleague Gorka Alcorta, who was presenting the molecular analysis, people attending, not him because he's here, but attending somehow. This is the facilities of the University of Navarra. This is a normal classroom of our students, and this is well, Dr. Manrique and Gorka and other attendees during lunch. These days that we have also the opportunity to visit our genetic facilities in ThimaLab Diagnostics, and also the facilities of the University Clinic, at the University Clinic of Navarra. It was a great time. Other activity or training topic was the dissemination for families, patients, and parents. We developed a special flyer for them. It's a model that can be adapted in countries and different centers. We just have this one that is about understanding the genetic of the deafness. It covers a little bit of genetic general information about the disease, the incidence, and so on. The classification according to different criteria. Also a little bit about causes, why we are deaf. We are frequently deaf. Why? Because normally genetic causes in this right arm, we can perform specific diagnosis that can be inherited in families. It can be inherited and passed to our children at different models. What we get when we test a deaf or other patient, we get much more than diagnosis. We are in the way of prevention to do prognosis of the clinical aspects of the disease. We can perform a personalized treatment. The patients must know if they can or cannot take antibiotics, or if they are going to undergo a specific treatment based on genetics. And of course, also for family genetic counseling, reproductive issues, and so on. Well, we explain also what clinical variables we have to take, how the genetic analysis is performed, and just like Marie-Noël and Manuel have already explained, which could be the algorithm that we think could help the diagnosis and the genetic testing of a child with a genetic hearing loss. Another intense, very long in time and very intense within the groups has been the training to perform mutation classification in our patients. We already knew about genetic variants, but for the specific case of deafness genes, we were very well trained in some of them, but not in others. We have a great opportunity to collaborate with Dreamgenics that did the tool and the portal. Here you can see the outline of a patient that it seems to be a pendred due to homozygous alteration of this gene. You can see a lot of filters. The tool has been already explained. Not only we trained in the platform and in the tool, we also have to train in a lot of clinical and genetic databases that brought the information about the clinical and the genetic aspect of the diseases that we were diagnosing. And it was a huge training and learning, at least for our group, and I think for everyone. I would like to finish before highlighting a thing that, at least for me, was a specific and wonderful training that was finally working in real multidisciplinary teams. With the clinical geneticists and the lab geneticists and the mutation curators and people dealing with databases in our institution, we met with our clinical colleagues in otorrinolaringology and audiology to cross the genetic and clinical information of the patients, which is the only way to do a good correlation between the clinical and the genetic findings, and being able, through the clinical geneticist, to reach the families and perform a good genetic diagnosis and genetic counseling, segregation of the mutation within the families, to set up follow-up measures by the clinicians, of course, and dealing with family issues like new children or what about my family now. Just to give a little brush about other activities, there are many variable. We were in the press, we were Manuel here in our television here in Spain. We have the wonderful channel of associated structures that were already working very well in our country, and also patient associations that were a wonderful channel for the dissemination of our findings. So I just wanted to say thank you to all attendees and to you all. And here is the web page that is also a dissemination and learning and teaching tool that we developed within the GHELP program. So thank you very much.
Thank you, Ana, for your support during this project and also for this talk. So we now continue with some recommendations for the future in the neonatal hearing screening programs, taking in consideration the results of this project. For that, I would like to show you what will be the recommendation in terms of how apply this tool in the normal neonatal hearing screening and diagnosis process, and also take in consideration the opinion of one of the experts in public health, like Maria Derra, that participates in this project and allows to the Instituto de Salud Laboral Pública de Navarra. So I'm going to share the presentation. Okay, so I am going to talk about these slides, and let me introduce, because it looks complicated, but I'll try to show you the main feature of them. So you can see here the time scale in months. So we move here from the newborn to the age of the 6 months. You can see during that time some of the questions or the moments related with the neonatal hearing screening program that happened between the 0 months and with months. So in that time, in most of the centers, the neonatal hearing screening happened. As results of these studies, we can have that some of the babies fail for that, and after this child is transferred to the hospital for the attention of the ENT specialist. In that time, the ENT specialist, we are around 1-2 months of age. Through the anamnesis, clinical examination, and first audiological assessments, they conclude for a suspicion of hearing loss. So it's in that moment where it's very important, even in terms to classify this hearing loss in acquired or genetic origin, just to split in terms of the results of the anamnesis, the clinical examination, and even the audiological assessment. So if we detect that there is no history of acquired etiology, we suggest in this point, so we are around 2 months of age, to apply for the gene panel, in our case, the GHELP panel, and follow this way, we can have 2 possibilities: that we have a negative results in the application and in the analysis of this genetic study, and again, by the age of 3-4 months, again, the child came to the ENT specialist and he complete the study with image examination, audiological assessment, hearing aid trial, and other genetic studies of segregation studies, just to classify in case that we have uncertain results in the variants that we detect with the panel. If we have a positive results of the application of the gene panel, we have 2 possibilities: that we have no syndromic hearing loss, and in that cases, the ENT in this period between 3-4 months can complete the study with image examination and audiological assessment, and will be ready to continue for the treatment and the follow-up after treatment of this child. In cases of syndromic hearing losses, ENT and other medical specialists proceed for image examination, audiological assessment, and additional tests, especially related with the syndromic causes that are associated to the hearing loss. In cases we have a positive history of acquired etiology, so again, the ENT address image examination, audiological assessment, and hearing aid trial, and at the end of the 6 months, this child can be ready to receive a final treatment, a follow-up in that cases. So I would like to remark that after the experience of this project, we understand that the moment where we can apply, taking in consideration cost, benefits, and other issues, the best moment to apply the gene panel is after this first examination of the specialist with the conclusion that there are a suspicion of hearing loss. I would like also to remark the importance of the cytomegalovirus test that necessarily must be performed during the first month of life of the child. So I think that is a very important test, especially to achieve a diagnosis in that cases when we are in the branch of acquired etiology of hearing loss. In the future, I presume that gene studies also can be performed during the neonatal hearing screening programs. We need to achieve tools with more efficiency. We need to achieve gene studies that will be semi-automatized or automatized interpretation of the results. And also we need for that reduce the cost of these panels. I would like now to introduce Maria Derra, that is going to continue with this presentation. Maria?
Thank you very much, Dr. Manrique, and greetings for all attendees and the colleagues of the project. In the field of public health, early detection in the context of organized population programs is one of the activities with the highest proven efficacy. Of course, not all diseases are candidates, only those in which there is reputable evidence. And this is the case of neonatal hearing loss, which observes all the conditions required for it. So, more than 20 years ago, neonatal hearing screening programs were launched in Spain and many more European countries. And it is well known how they have contributed to improving the prognosis of children with hearing impairment through early diagnosis and treatment of deafnesses. But also, since their inception, programs have improved in the different countries or even regions. The programs are considerably varies in the organizational model and the screening techniques and protocols used. And what remains to be overcome is the fact that all of them are focused on symptomatic treatment and therefore palliative. So a paradigm is necessary to change. And in this way, is what this project intends using the GHELP genetic tools to be able to reach an etiological diagnosis of deafness, which may allow in the future the possibility of a personalized early treatment. That ways, there are already very helpful experience in this area. And on the other hand, this study, as we have already heard in previous presentations, has yielded good results in terms of direct cost savings, consultations and tests avoided, indirect cost, lost working hours by parents, for example, and intangibles too. In other words, a positive cost-benefit balance has been demonstrated. Please, next, Dr. Manrique. Although these first results obtained in the GHELP project are important and very encouraging, we are not done yet. We have to finalize the pending studies and disseminate the results in the different areas of interest, and also over time optimize the tool so that a greater number of genes will be included, cheaper, better automation of the results is achieved, and the sensitivity of the technique is increased, reducing uncertain results. In short, that the cost-benefit balance would be increased more. It is the responsibility of public health to organize and ensure the quality of current population screening programs, as well as to support initiatives that try to improve them. Is their obligation, and in this spirit, the Public Health Institute of Navarra has participated in this project. The results of the project are encouraging. Also, the implementation of the genetic tool and the study still has important challenge to solve, such as the exact identification of the better time and the specific target population to which the tool can be used. The validation of this strategy as the most efficient possible. The guarantee of the feasibility of its implementation. Please, next, Dr. Manrique. At the moment, public health is contributing with the rest of the teams to generate scientific evidence, and we do want to continue doing so. For this, we consider that it's necessary to carry out more studies in the real world, so that a medium-term proposal could be, once the last analysis and scientific production have been finished, could be to carry out a pilot project in a newborn genome screen program, specific newborn genome screen program, including the GHELP genetic tool. This would allow to test the genetic tool in a real context, to detect possible failures of problems that may arise, to find other beneficial effects not discovered at the moment, to evaluate the result, and all above consider the possibility to issue stronger recommendations. Thank you very much.
Thank you. I don't know if I have the okay. So thank you very much, Maria. So Maria has to do a trip right now. I don't know. We have at the end an open round questions time, but maybe if somebody can do a specific comment or question addressed to Maria, I think that is okay, yes, to do that. So you can use for that the chat, and we'll try to have the answer of Maria. So so we take care about the chat for the next time. We continue with the program, and we move to another very important area. So we are working for the interests of the patients and families of the children that are involved in these neonatal hearing screening programs. I think that is important to take in consideration the role that they play in all this process, and is why we include Deaf Association in the project, and it's for me a pleasure to have some of the representatives of this association in this final event. So I would like to to introduce first one of the families that cooperate in the project, but before give the word to this family, I would like to introduce one of the videos that allows specifically to this family.
Cuando nació, hace casi 8 años, nos dijeron que tenía una sordera en ambos oídos de tipo severo, y la característica es que es una sordera asimétrica, es decir, que los tonos graves los oye por su propio oído, pero a medida que vamos a frecuencias más agudas, pues la caída aumenta. Realmente no fuimos conscientes de que no oía, porque en casa la niña sí que reaccionaba a ciertos sonidos ambientales, a ruidos.
Y entonces estás en una situación que como padre crees que o quieres que oiga, y de todas maneras las pruebas te van diciendo lo contrario, ¿no?
No teníamos ningún factor de riesgo, digamos, que nos hiciera pensar que nuestra hija podía nacer sorda. O sea, fue algo totalmente inesperado.
Pero bueno, yo me considero una persona optimista y desde el principio pensé que había que hacer todo lo posible porque Laura saliera adelante.
Nos pusimos en manos del doctor Manrique de la Clínica Universidad de Navarra. Con 3 meses y medio de vida le pusimos los audífonos.
Y realmente notamos una diferencia. Nos dimos cuenta que no teníamos muchas fotos, ella sonriendo. Y fue ponerle los audífonos y empezó a sonreír. Ahí es donde realmente nos dimos cuenta que efectivamente tenían razón.
También nos aconsejó que nos pusiéramos en contacto con la asociación EUNATE de aquí de Navarra, que da servicio y apoyo a las familias de personas con sordera, y allí también empezó sesiones de logopedia, y con 4 años el equipo del doctor Manrique de la Clínica Universidad de Navarra consideró que era oportuno implantar uno de los 2 oídos.
Y realmente el implante dio ese salto a que Laura hiciera más cosas auditivamente hablando, ¿no?
Semana a semana iba hablando mejor, iba hablando más, y entonces ahí realmente ya íbamos viendo que estaba funcionando.
Y de hecho Manrique nos dijo que el segundo implante coclear lo decidirá Laura si lo quiere o no lo quiere, ¿no?
No sabemos cuál es la causa de su sordera. En el momento en que nació nos hicieron un pequeño estudio de 2 genes, que son los que en ese momento se miraban, salieron negativos y entonces se queda en el aire.
No sabes si va a repercutir en otros hijos o en el futuro si quisiera tener también hijos. En el caso concreto del proyecto GHELP, que es un proyecto interregional que lo que quiere es acercar la investigación a la sociedad, hay una colaboración de 8 entidades que están trabajando para el desarrollo de un panel de diagnóstico para una enfermedad que afecta a 5 de cada 1000, según la OMS.
O sea, que todo lo que se investigue creo que es un bien para la sociedad y para estos niños.
A día de hoy es capaz de tocar el piano, le gusta la música, baila, le gustan las películas, es capaz de todo, de todo.
La vamos a apoyar, si le gusta seguir con la música, si le gusta lo que le guste.
Tenía una flauta que le regaló su tía abuela y siempre venía con la flauta diciendo que estaba rota, y a raíz de que le pusieron el implante me vino un día con la flauta y me dijo: papá, ¿has arreglado la flauta? Y digo: no la he arreglado, lo que te han arreglado es el oído a ti.
So it's a pleasure to have Andrew and the family of Laura here. So please.
Okay, good morning, everyone. I will try to do my best. I really love this video, and Josu de Pablo did a great work, and really it has been a wonderful gift from GHELP. Thank you so much. First of all, I would like to thank Dr. Manrique and his entire team, not only for being able to be here today representing the families of people with hearing loss, but for all the work that they do every day at the Clínica Universidad de Navarra. Also, I would like to thank my colleague Iciar Gomez, both for inviting me to this event today and for her management work in the GHELP project. I know she did it pretty well during these last 3 years. Let me come back to the video that we have currently watched. It's true that when I watch the video, I can stop getting excited. And it's certainly a beautiful story told from a beautiful point of view. But the story itself has a great side to it. I still remember the day that Dr. Manrique told us as the first time that Laura had hearing loss. And we couldn't believe it. The world fell upon us, questions, doubts, answers, fears appears. It's funny, but in a matter of minutes, the possible future that awaits Laura was represented to me in few seconds, probably due to this lack of knowledge about the world that surrounds hearing loss. And we thought about all the limitations that could affect Laura's life. At that moment, it doesn't matter what they told you, you're still in shock. But Dr. Manrique was very clear at that time. He said, Andrew, Maria, calm down. Your daughter has a future ahead and she will be able to speak fluently. You will probably have to silence her. And he was totally right. It doesn't matter. He was totally right because, of course, thanks to the great effort by the multidisciplinary team, parents, family, medical doctors, specialists, and speech therapists, and of course, Laura. I think that the worst part is the initial one, and they usually call the mourning period. And it's true, you need to assimilate the new situations that change your perspective of life, and you usually cry a lot. But once this period is over, you see everything with other eyes. It is very important to start early with the rehabilitation and start to work, and there Laura was flawless, totally perfect. Undoubtedly, the family framework and the social environment is crucial for the evolution of the children. At that moment, a beautiful profession arises in your life, is the speech therapist, a key piece in this puzzle. And here, I would like to make an important mention. I want to thank the Asociación EUNATE here in Navarra for all the support we received from them. And also to María Ángeles Soler, who has been working with Laura since she was only 4 months old. We believe that it's essential to contact associations or patients or family that have a similar situation. Being informed from the first moment is crucial. In our case, and after 10 years, Laura is in 5th grade at school and she gets really good marks. And she's a great ballet dancer and she plays the piano in an extraordinary way. But anyway, I'm his father, what I'm going to say, no? But so far, this could be a quick summary of these last 10 years. But let's talk about why we are here today. I think science, technology, and innovation. Along these lines, I would like to tell you a story that we lived with Laura once at home. And one day I was telling her how wonderful life was back in the 70s or the 80s, without stress, without mobile phones, without so much technology, no? And do you know what she told me? She said, yes, Daddy, you're maybe right, but at that time, there were no cochlear implants like there are today. And therefore, perhaps I will not hear her speak as I do today. She left me speechless, and I answered her, you are totally right. What I'm trying to explain with this example is to confirm how important science is, how necessary it is for the good of society, and of course, for patients and families who always need to have a solution to something. Currently, there are technological and methodological solutions that are applied to deaf people, and they are really effective, but like everything else, there are still more ways to go. 3 years ago, it started a beautiful project called GHELP, which will offer the opportunity to study with a simple blood sample the 180 most relevant genes related to hearing loss. What is achieved with this? From a scientific point of view, we can imagine that maximizing diagnosis time and facilitating early intervention in the patient that we have seen today that is very important. From the point of view of the patient or the family, clarifies in some way why your son or daughter has hearing loss. And it's funny because when you go to the hospital and see other parents with their kids in the same situation, after talking for a while, one of the questions that arises, and do you know what the reason is? And generally, it is usually a resounding no. I think that the outcomes of the project may be able to clarify this question that arise in many families. And probably other questions. Without a doubt, it will significantly help early intervention in the patient, which has been seen to be crucial. The sooner, the better, and of course gives very useful information to the patient and their families. Therefore, when Dr. Alicia Huarte asked us if we want Laura to participate in the project, we did not hesitate for a second. We say yes. And not only for knowing in some way if Laura's cause is genetic, but for contributing in some way to the project. Because today we're talking about genetic panels for the diagnosis of hearing loss in patients. But what is certain that in a short time, and thanks to science, we will be talking about real treatments for hearing loss. I don't know, cell therapy or gene therapy, who knows? Which is sure that I will very much like to see that. And that's why I believe that financing programs such as Sudoe itself or other European Horizon Europe programs are very important. Science to provide solutions to society, especially for the patients and their families. For this reason, the GHELP project is a clear example of a scientific project whose final objective is society, and for sure, the patient and their families. Therefore, as a representative today of the patient here today, I want to thank the team of doctors, scientists, specialists, technicians, and managers who have been able to make this collaborative project a reality. Of course, also to the Sudoe program for choosing and financing the GHELP project, which I know was chosen among many within the Access Panel 1. I think this project probably reflects the essence of this axis itself, research and innovation. And finally, I would like to thank my wife, unconditional support, and who has been my travel partner in this, we can call it adventure, with ups and downs and crying and laughing at the same time. And of course, Laura, for your great effort. You did extraordinarily well I still remember your first speech therapy with Maria Angeles when you were only 4 months old. You have been fighting and working without ceasing until that day. Thank you, Laura, and thank you all.
Thank you very much, Andrew. I really are emotionated with your words. Well, it's the turn of Mr. José Luis Aedo, that is the president of the Spanish Confederation of Families of Deaf People, FIAPAS, that strongly work and believe in this project. And I would like to give thanks and also give the opportunity to speak in this final event. José Luis.
Thank you, Dr. Manrique. Good morning, ladies and gentlemen, dear friends. Let me remember you that tomorrow will be the International Day of Deaf People. Once again, I would like to thank the members of the Interreg Sudoe GHELP project for inviting the Spanish Confederation of Families of Deaf People, FIAPAS, to participate in this journey, which will undoubtedly benefit deaf people and their families. Let me briefly introduce the organization of which I am president. FIAPAS was created in 1978 to provide answers to the needs of the families of people with a hearing disability and of the deaf persons themselves. At present, it is a national confederation made up of 47 local and regional organizations which constitute the largest platform for the representation of families of deaf people in Spain. FIAPA's purpose is to build an inclusive society where people with deafness and their families are the protagonists of their own lives and decisions, exercise their rights and participate on equal terms. We work for integrate and promote the action of our associative movement to represent and defend the rights and global interests of people with hearing disability and their families, promoting awareness of the value they bring. For FIAPAS, the early detection of childhood deafness has been and continues to be a vitally important concern and occupation. For this reason, in 1992, we participated in the multicentric study for the detection of hearing loss in high-risk population, carrying out research work without precedent in our country and whose results, published in 1994, marked before and after in the health field in relation to hearing loss in childhood. The study provided data, both epidemiological data and data on the prevalence of this sensory loss, that had been lacking in Spain until then. In 1995, following the publication of this study, and after conversations with the Health Administration in Salud, who expressed their interest in continuing their work began, it was decided to create a scientific working group called the Commission for the Early Detection of Hearing Loss, CODEPE, whose general objective is to disseminate and promote the early detection and diagnosis of childhood deafness in Spain. CODEPE is composed of 2 representatives of the Spanish Society of ENT Doctors, 2 representatives of the Spanish Association of Pediatricians, and 1 representative of FIAPAS. Since its beginning, CODEPE has developed different actions aimed at promoting the early diagnosis of treatment of deafness. In 2003, this work led to the Ministry of Health, together with the autonomous communities, approving the early detection of deafness program for its implementation throughout Spain. FIAPAS is deeply proud of this fact, which has not preceded in Europe, as it advocates a global approach to deafness and includes not only early detection and diagnosis, but also the stages immediately after the diagnosis, for example, hearing devices fitting, and speech therapy intervention, as well as individualized monitoring of each person with a hearing disability and family counseling. After more than 40 years of activity, FIAPAS, in its commitment to deaf people and their families and to continuous improvement and renewal, also does so with innovation and scientific advances. Therefore, our commitment to develop alliances that are beneficial to deaf people and their families have led us to participate in projects such as GHELP, which will, with no doubt, contribute to promoting the future of early detection of childhood deafness. Among the challenges faced by the results of this project, in which FIAPAS has participated as a member of the External Advisory Board, is to focus once again on the need for families to know the diagnosis of their children as early as possible, to consequently improve the treatment and prevention of deafness. For FIAPAS, it is also a priority that this has been insisting on for many years. The need for coordinated interdisciplinary work between professionals involved with children with deafness and the family representative movement, especially considering the priority role that families play in the education of their children at the time involved in the long journey and migrate through various professionals and specialists. Therefore, when among the challenges of the GHELP project is proposed the creation of support structures for families, we are blessed to recognize that in Spain this should not be a feature, but a reality in which FIAPAS has been working for more than 43 years, particularly since 1998, when we implemented a specific program of attention and support for families. It is a network of 43 professionalized services where families who have just received the diagnosis of deafness in one of their members are welcomed, emotionally supported, informed, and trained. In addition, early attention and specialized speech therapy intervention is provided. We are then at an advantageous situation to begin to face the future challenges posed by this new line of detection of childhood hearing loss based on genomic diagnostic tools, because it already exists a solid, distinguished, and experienced entity that brings together, supports, defends, guides, and accompanies the families of the people. And it also leads the political and social advocacy, supported by a high-level technical work for the implementation of early detection of deafness programs, the development of the necessary benefits for hearing devices fitting and rehabilitating treatments, and pushes for collaborative work with all the agents involved from all levels. Therefore, FIAPAS values and supports anything that contributes to improving the quality of life of the people and the exercise of their rights. Thank you very much.
Jose Luis, thank you very much to be there, to the big support from the institution that you address. Well, we move to the contribution of Luisa Monteiro. Luisa Monteiro, she's working in Hospital Luisadas in Lisbon. She is one of the external evaluation advisory person that will contribute in this project. So Maria Luisa, thank you very much to be there, and go.
Good morning, everyone. Firstly, I would like to thank you a lot to Professor Manrique and his team for inviting me to participate in this very important project. We know that around 500 million people worldwide have hearing loss, and 34 million are children. Since the last few years, since 2017, the World Health Organization has put a very important stress in defining rules to address hearing loss in the whole world. We estimate that in the Southwestern Europe region, where we live, we have around 250,000 children with some degree of hearing loss. And we know also that 60 to 80% of all cases of hearing loss are related to some genetic disease. And we know also that in developed countries, hearing loss that is caused by genetical diseases is the most prevalent. We know also that we can see hearing loss as the only feature, or it can be associated with other problems. And most of the genetic hearing loss and most of all cases of hearing loss are prelingual or perilingual, which accounts for the negative impact of unrest hearing loss. So genetic testing can be very important for diagnosing the cause of the etiology of the hearing loss. Also for prevention, secondary prevention of the hearing loss. It can also help to identify the prognosis in every single case. And perhaps in the future, it can also help personalize the treatment of every child that is diagnosed as having a hearing loss. Family counseling is also very important, and some families must make decisions without knowing what is the etiology of the hearing loss of their children. So GHELP, being a transnational research cooperation project, is very important. It aims to innovate in the field of early detection, diagnosis, and treatment of hearing loss. The main object, as it has been said before, is to promote the innovation and the early detection of hearing loss in children, introducing a genomic diagnostic tool in current screening programs. And with that, we'll think it will enable to move towards the personalized medicine in the treatment of this kind of disease. So the specific objectives of this program are: the first one, to develop a tool that is important, a panel of genes that can allow identified in one test the most common 180 genes related with hearing loss. It also tries to understand the economic, social, and clinical feasibility of incorporating the sequence testing with the current hearing loss detection programs. And also it tries to reduce the knowledge gap in genetic hearing loss diagnosis that still exists in general public and also in the professional health people. And the results of this study are very impressive, especially when we think that most of the study was conducted during a major pandemic period. So it was able to recruit almost 500 samples. 500 of children were enrolled, most of them in the retrospective group. And the retrospective group enrolled 431 children, and of course their families. And the prospective group, the prospective arm of the study, enrolled a less smaller number as we expected. 62 children were enrolled. And most important, I think, it is the capacity of putting different countries in different center experiences working together. So I will try to see with you, especially the experience of the center in Navarra, who was able to diagnose 50 patients with selecting among them all, and they could diagnose 50 patients as having some genetic mutation that was identified as responsible for the genetic hearing loss. And as we expected, the connexin gene was the most prevalent among the 50 patients diagnosed, followed by otorrinolaringología and myosin gene. In Navarra, also the retrospective group was different from the prospective group, considering the amount of cases, the percent of cases that were diagnosed as genetic. And we can see that the prospective group had a higher sensitivity when studied by the genetic panel. And perhaps in the future, if we test early, perhaps this bias between the retrospective and the prospective group can disappear, and perhaps we will be able to diagnose most accurately and earlier the genetic defect. It also they also were able to prove the cost benefit of applying the genetic test to the standard newborn hearing screening program. And perhaps this can be generalized to other programs in other centers and in other countries. But we can see that in Navarra, applying the genetic test at the same time as the audiological screening, they could demonstrate that the costs can be almost halved. And this can be a very important public health issue. Also, many professionals were able to attend formation in presence or in remote programs. So this objective of diminishing the gap between the knowledge and the state of the heart in the genetic aspect of hearing loss was also achieved, as well as the dissemination actions among the general public. There has been lots of initiatives involving the media in the different countries that help to enlarge the view of the general public toward hearing loss and what we can do nowadays to early diagnose and rehabilitate children with hearing loss. So there are very strong aspects of the project that need to be commended. One of them is the large number of cases that were enrolled in this study. And as we expected in the first stages of the study, more cases were enrolled in the retrospective arm of the project than in the prospective arm of the study. Also, we need to commend the capacity of coordination of the different centers located in 3 different countries in the southwest of Europe. The strong aspects of the project were really being able to achieve all the 3 different specific objectives. The development of the test of the next generation sequencing test could be proved, as could be also proved that this test is very well adapted to the southwest population of hearing loss children in Europe. It also proves that it is feasible and cost effective, at least in one of the centers, to incorporate the screening of the genetic defect in the current hearing loss screening programs. And also, it will contribute as well to reduce the gap in the knowledge of the genetic hearing loss diagnosis. And I think that in the future, these 2 last aspects can also be improved and developed. So, evaluating externally this project, I would like to say that there are some goals yet to be reached. Perhaps the most important goal that needs some further investment is translating into clinical results what was found in the genetic analysis of most of the children enrolled in this project. So much more time and investment is needed. And I think that this effort will be the most important clinical aspect of the project. And also the cost-benefit model that was used and proved in Navarra should be replicated in other centers. Other centers need to prove that perhaps introducing the genetic test very early in the flow chart of the diagnosis would be cost-effective and important for the families. Also, the dissemination of the results among the scientific community and all the other stakeholders of this aspect needs also to be developed. And I think that today we are also contributing to disseminating the results to a large community of people, doctors, families, and associations and other technicians. So my overall evaluation is that this is an extremely important project. And this will have a very important impact in the future of the organization of the newborn hearing screening programs in Europe and perhaps around the world. And I think also that the future utilization of the GHELP panel for genetic diagnosis of the hearing loss will improve the efficiency of the etiologic investigation of the hearing loss, involving less money, less time, and less anxiety for the families. So my evaluation is extremely positive, and I will also congratulate the team and thank them for their extraordinary effort in putting together and developing this project. Thank you for listening.
Thank you very much, Maria Luisa, for your talk, and I take note about your recommendations. I am sure that we are in the beginning of a long way. I'm sure that with cooperation of people like you and most of our colleagues will at the end incorporate this kind of tools in favor of our families and our patients. So I think that we are on time. So it's unbelievable to be on time, no? In one of the in a meeting, no, scientific meeting. We have some time for questions. Through the chat, I received one question related if we test cytomegalovirus infection in our project. The answer is that only we make a question to the different hospitals to know if in the prospective group the people included has been tested with the cytomegalovirus. So about 50% of the childs in the prospective group were tested, but none of them saw a positive result. So in general, we like to mention that it's a very important tool to achieve etiological diagnosis of the hearing loss, plus we mentioned the genetic studies. So I presume that in the future we'll need to use both kind of tests. One to test one of the more frequent acquired hearing loss causes, that is the cytomegalovirus infection, and also the genetic test. So I think that both will be part of the future in neonatal hearing screening programs and in the future of the best treatment for the child that has a hearing loss due to these causes. ¿Tenemos alguna pregunta? Well, it's time for questions or comments. Please go ahead. Otherwise, so I would like to give the final word to Javier Mata. So Javier Mata is the director of the institution in our university that allow the force to innovate and to go forward with the research commitments in our university. So please, Javier, you have the word. Well, Javier is trying to connect, so we wait for some minutes. No? If you have, in the meantime, some questions. So there are some people give thanks in the chat, give thanks for the meeting. So also I give thanks to be there. So it's very important the dissemination of these results as happen in general in science. So it's a community. The people is working in medicine, in biological science is very, very important how from So I don't know, Javier is there? Oh, yeah.
Dr. Manrique.
Javier.
Dr. Manrique.
Yes.
I have said, no, yes. I'm José Luis.
Ah, José Luis,
I have shared some news in press. We are impressed yet.
Mm-hmm. Oh, thank you. So in the you have in the press, no? Maybe some news is coming from the project, no?
Sí, yes. Okay.
Okay, thank you very much. So somebody like to open the chat can find some email address or web page where you can find some new that they are into the press. Yeah. Well, I don't know if finally Javier is there.
Yes, I'm here.
Okay, thank you very much. Yeah.
I'm here in San Sebastián.
Yeah, you have the final word, so go ahead.
Thank you. I would like to start this closing session or this session by thanking your attention, your attendance, as well as participation in this event. All of you actively in the hearing loss area from different perspectives and sectors, attending patients in hospital, giving advice and support services through associations, or developing public health policies and specific screening programs. It's very remarkable to have all of you come and work together. I think that this is the best thing of this project, with one goal in mind: improve the quality of life of people with hearing loss. According to the World Health Organization, by 2050, it is estimated that nearly 2.5 billion people will have some degree of hearing loss, and that at least 700 million people will require hearing rehabilitation. So this is data from ITSIAR. Thank you very much, ITSIAR. As we have said this morning, hearing loss is a public health problem beyond economic losses, given that untreated hearing loss can significantly impact on the person's quality of life. Advances on hearing loss prevention, as well as screening for early identification, early intervention, and rehabilitation are completely necessary. And this can only be achieved by cooperation among all agents involved in all these activities. After 3 years of hard and dedicated work, GHELP project comes now to its end. During this adventure, we have learned a lot from each other. We have cooperated, shared knowledge and resources, and we have achieved important results for patients, the more important, their families, and health public administration. We sincerely hope that the GHELP genetic panel will help to advance in the hearing loss diagnosis and understanding the genetic origin of this disease within our community. This will have not been possible without the 8 participating organizations in the project, our associated partners, and of course the financial support of the Interreg Sudoe program that trusts on our project idea. Although the project ends now, we will continue working in this field, even more motivated and committed to help people with hearing loss. On behalf of the University of Navarra and the Clinic of the University of Navarra, thank you again for your attendance to this event, and we hope you find the sessions interesting and useful. Thank you very much.
Thank you very much. And well, this is the end of this event, but as you say, we continue. Go deeply in the results we obtain and sure with a new initiative, because our commitment, the main commitment, is to help people with hearing disabilities. So thank you very much again, everybody. from the different size of these projects, from the people that works like technicians, ENT doctors, etc. and etc. and etc. So it was a pleasure to be with such a wonderful team. Well, thanks, and you have my gratitude for that.
Thank you so much.
Thank you very much.
Thank you.
Bye. Bueno,
Thank you all.
salimos, ¿no? Hello.
Then,
Thank you.